One of the main reasons that we're looking at reaction order and rate laws and reaction rate in general isn't just to speed up or to slow down things, but to understand the process of how reactants turn into products. So the collision model is super helpful, but the collision model doesn't necessarily account for all of the different ways that the process can occur. Or if we think about something as maybe being zero order or second order, and we change the concentration, it wouldn't explain why increasing the concentration might have a bigger effect for something that's second or third order, or why it might not have an effect for something that's zero order. So when we try to do that, we need to really understand the step-by-step process of the reaction to understand the rate, the order, and the rate laws. When we do that, we are talking about elementary steps or elementary reactions. Those are the individual, sometimes they're described as collision events, or the individual steps that occur throughout the process. They are the individual bond breaking and bond making processes, and they can't be broken into any smaller steps. Sometimes mechanisms are just 1 to 2 steps. Very often they're in the 2 to 4 step range, but sometimes they can have even dozens of steps. The catalyzed process of turning nitrogen and hydrogen into ammonia is broken down here into 10 elementary steps, even though it's just the simple idea of turning that reaction. When we're thinking about elementary reactions, we really focus on how many molecules are colliding because that makes a connection and allows us to understand the collision model. When I just have a single element or a single molecule breaking into some products, we would call that a unimolecular collision. So right here, they show our some of our components weird here. But when it's just one thing breaking into multiple products, that is unimolecular. And we can create a rate law for that elementary reaction. With elementary reactions, the nice thing is that the rate law is directly proportional to the concentration. If I have more of substance A that is breaking apart, the reaction or that elementary reaction will go faster. The easiest to envision is a bimolecular reaction. When A hits B and turns into product, or an A hits another a molecule runs into itself. That is bimolecular. Two things are colliding. And once again, it is directly proportional to the concentrations. So if I put in more A or I put in more B, A collides with B faster, B collides with A faster, and my rate increases as a result. Same thing with A and A, which is where we kind of come up with the idea of how something might be second order. It collides with itself during an elementary reaction throughout the process. It is possible to go beyond that, but we're not just talking here about three chemicals as reactants, but three chemicals simultaneously colliding with enough energy, with the correct orientation to break and to make bonds. It is possible, but it's very rare. And reactions that have a termolecular step tend to be slower because of how rare this is. It could be A with B and C, or it could be two A's with the B, A's with itself, or any combination thereof. So it could be a chemical that is third order relative to itself. It needs to run into itself three molecules or three atoms at a time in just the right way. Or we can break down into things that are first order relative to each, or a combination of first or second. So each of these is just the one thing that happens to go not from point A to point B, from point A to A1, and then A1 to A2 to A3 to A4 before we get to B. The very subtle changes we see along the way before we end with our ammonia. And understanding these elementary reactions is important because it's how we put them together to understand the overall process. That overall process is called a reaction mechanism, and it's the individual steps by which our reactants break bonds and make bonds to ultimately end as products. And investigating the mechanism allows us to understand that process of change and connect a rate law and a reaction order to the experimental data. in a way that does directly use and apply collision theory. During that process, sometimes, and we can see some things here, things pop up that we wouldn't consider reactants or products. For this one, we said it was nitrogen and hydrogen making ammonia. N2H2, NH, and NH2 are not reactants nor products. So they're not in the overall balanced equation, but they are in elementary steps. A catalyst would appear in elementary steps and would appear in the mechanism. They speed up the reaction without being consumed, meaning that we don't have to write them as a reactant or product. So, in terms of a mechanism, a catalyst would be used in one of the early steps. It would collide, it would react, it would be involved in the breaking and making of the bonds. But then in a later step, we would remake it or recreate it as a product. So overall, although it's used, it doesn't change, it doesn't have a net change. Some that I pointed out up here, NH, N2H2, and NH2 are intermediates. They are made at one point, but we don't end with those. That is called an intermediate. Intermediates are present only during the reaction. And if we can detect an intermediate with experimental data, we can kind of prove that one mechanism may be more reliable or more correct than another. But what our goal is with mechanisms, and we've got a lot of bullet points below this, is to understand that step-by-step process, to really think about which bonds are being made and broken when, which allows us to control the reaction more, or at least to investigate it at a deeper level. The important idea here is that our mechanism connects with the rate law and our mechanism connects with the reaction. So for a mechanism to be correct, or at least to be supported, first of all, they have to match the reactants that we're talking about. So when I put all my reactions together and cancel them out and combine them, they give me the overall reaction. We could cross out N2H2s and NHs and NH2s and all of those and see, this one's a little sloppy, but we'll see it later, how it does add up to this reaction. The intermediates would cancel out, the catalysts would cancel out, and our total reactants would add up to our total products. The other piece to that is if there was a catalyst, it could appear at the beginning, and we would want to see it at the very end. A lot of times, and I didn't specifically mention it here, it may ask if a chemical is a reactant, a product, an intermediate, or a catalyst. And it's all defined by whether it is consumed by the overall reaction in the mechanism, it's produced by the mechanism, it is consumed and then reproduced, which would be a catalyst, or produced and then consumed, which would be an intermediate. And those are good words to use in your description. The other and probably more important part is that the mechanism has to be supported by the data and the experiment. When we go through a multi-step process, some of them will go really fast and some will go slow. A classic example would be like baking a cake. Mixing things up might go fast, but baking it would take a little while. Then cooling it would take a while before we could frost it. So it doesn't matter how many bowls you have to mix things up. There is a limit to how many cakes can be baked based upon how much space you have in your oven. When we're looking at this in terms of a reaction and a reaction mechanism, there is one step that takes longer than any of the others. We call it the RDS, or rate determining step. It is the elementary reaction that is the hardest to complete. It has the highest activation energy, maybe because it's got the strongest bonds, the highest, the most energy that needs to be used to do that. Maybe there's something with the orientation. Maybe it's termolecular and you got to get 3 molecules just right. But it is the least likely to result in a successful collision. We don't necessarily know that by looking at the reactions, and that's where it comes back to matching the data. Very often, the first step may be the slow step, and that means that the rate law for the whole reaction is determined by how fast that first step can go. And since the rate law of an elementary step directly matches the stoichiometry or the coefficients, we can look at the coefficients on each reactant in our first step when it is the slow step and match that with our order. But if the first step is not the slow step, we have to think about all the steps that happen before the slow step and include the slow step. This is a hard process to be able to put into words, so this is probably the most important thing to look at and look at the examples. So we would include all of the steps and we would count how many times does everything appear, and those are how many molecules collide, which is what impacts it as 0, first, second, or third order overall. A catalyst might show up in our overall rate law because the concentration of that catalyst may determine how fast our reaction goes. The concentration may not, so it may just be the presence of the catalyst. Intermediates will never be included in the rate law because we cannot control how fast they are created. We cannot manipulate their concentration. Therefore, we cannot see how they connect directly to the rate. So here are the examples, but coming back to this, we are thinking about individual collision steps, and only for those individual elementary steps do we look at the coefficient to determine the order. But when we put all of that together and support it with experimental data, we can think about how a multi-step process may be used and supported to know the step-by-step reactions that support a reaction, an overall reaction rate, and specifically a rate law with specific reaction orders.